Hello everyone, welcome to this Cavity QED Lecture series. My name is Songtao Chen. I'm an assistant professor in the ECE department. Today I'm going to talk about or introduce about our research on cavity-coupled telecom atomic source for quantum networking applications. So here is the list of all the lectures in this Cavity QED Lecture series. So there's a lot of different aspects of Cavity QED related contents research happening in the RISE. Okay, so so this is what we're gonna talk about today. So I designed the slides in a way that I would not go too deep on a certain topic. I want to give you a more kind of broader overview of what we are doing. And if you have further questions, feel free to schedule a meeting with me or chat with my graduate student. We can talk a little bit more deeper on the topics. Okay. So first of all, this is my group. I have a few graduate students actually presenting here. All the hard work are done by my students. Okay. So since we are talking about quantum network, so what is quantum network? Okay. So I assume everyone here is familiar with the classical network, right? Wi-Fi or some 5G network, right? You have different nodes, and then you have some signal kind of helping you transmitting information between the nodes, right? The quantum version of this is very similar, right? You have the nodes, but now instead of classical nodes, you have quantum nodes, okay? We'll learn a little bit later why we call it quantum nodes. And then you have channels connecting them. Okay, this can be fibers or can be even just free space, right? You can send a laser beam. If it's free space, no obstacles, the laser beam can reach from A to B, right? And then in this quantum networking infrastructure or framework, typically people use single photons to carry the quantum information to move from A to B. And this single photon typically will be entangled with some other qubits on your local nodes, right? For example, a spin. And this photon can propagate through the channel, quantum channel, and then convey or carry this quantum information from A to B, okay? So you may wonder, we already have very fancy classical networks, right? 5G, nowadays people are talking about 6G. Right? Why we need quantum version of this? So there are a few arguments. The first argument is about the quantum mechanical version of this can actually give you like security that does not have a counterpart in the classical network, and this is just protected by how quantum mechanics work. Okay, so you probably heard of things like quantum no cloning theorem, and you probably also heard of that wave function can collapse during the measurement, right? So all those quantities can help you to know if there's an eavesdropper trying to steal the information between the A and the B, okay? So for example, this is a very famous communication protocol called BB84. Essentially what it does is that it encodes the information in the polarization of the single photon. And then by sending this series of single photon from Alice to Bob, they can extract the key or the secret information they want to send. And as long as there is a eavesdropper in the middle trying to measure and steal the information, Alice and Bob will have a way to know, okay? So this is what quantum mechanics can give you that classically you cannot do. The other argument comes from this quantum computing regime. So as you may know, nowadays the development of these quantum computers is getting like faster and faster. If you track like how many qubits people have demonstrated in the quantum computer, it really increases in a fast pace, okay? But people also realize that it is really challenging if you want to, say, incorporate a large number of qubits in a single quantum computer, okay? So for example, now like in superconducting qubit where IBM and Google are pursuing, they can get, say, 1,000 qubits on a single quantum computer. And then the other platform using neutral atoms, people have demonstrated using rubidium atoms to demonstrate this quantum computer. Here you have 48 logical qubits, but remember these logical qubits actually are encoded by physical qubits, so the actual number of physical qubits is much larger. Okay, so now people know that you cannot really build up a single quantum computer that has so many qubits. How are we going to do it? Okay. Let me come back a little bit. The reason why we need so many qubits is because the qubit itself is very noisy, right? The qubit error rate nowadays is on the order of 10 to the minus 3 to 10 to the minus 2, right? And then to counteract these errors, people need to do this thing called quantum error correction. But to do the quantum error correction, you need more physical qubits to do the encoding and then to do the operation there. That's the reason why people create this concept called quantum volume, where you combining these two factors, right? So on one hand, you need the qubit to be less, to have less error, and then on the other hand, you want the number of qubits to be large. Okay. So with this background, one thing people have thought about is to combine kind of different quantum computer on a network. Okay. So you can think that, okay, I don't know how to build a 10,000 qubit device on a single quantum computer. How about I build 10 of them? Each one has 1,000 qubits, which I know how to build it. And then I can use this network to connecting them together. And then combine all the resources together, you can achieve performance that really needs 10,000 qubits to do it. Okay. So people have started to think about this, right? There is some both theory and experimental work on this distributed quantum processing units networking thing, right? So here the two theory paper, one coming from the neutral atom platform using the ytterbium, and the other one using the trapped ion, the calcium, both of which kind of using these 2 or 3 or more than that, these quantum processing units to try to connect in them via some protocols. Experimentally, there's a work coming out last year from Harvard where they actually using this defects in diamond called silicon vacancy, and then they build up a network, I think in Boston area, around like 35 kilometers long, and then they establish some communication between the two SIV in the experiment. Okay, so to summarize a little bit, there are two motivations. One is we can get more secure communication. The second one is this quantum networking can help you to build up larger quantum systems by connecting these distributed QPUs. So to make large quantum networks, if you are using the fiber, one thing you need to worry about is the transmission loss in the fiber. Okay, so we have this classical communication based on the fiber optics, right? In your home, the Wi-Fi signal probably is coming from a fiber, and then there's a demodulator, and then generate the Wi-Fi signal at the home. So if you're using the fiber, the transmission loss is an issue, right? So here you can see this fiber attenuation at different wavelengths, right? So the loss in the fiber mostly limited by 3 things. One is the Rayleigh scattering, one is the IR vibrational mode absorption, and then the other one is this OH, which is people call it like water peak in the glass. Okay, so you want to find the platform that can have low attenuation in the fiber, so that you can go longer distances in your networking effort without worry the decay too much. Of course, at the end of the day, for example, even you are at the lowest point, right? We're talking about something like 0.2 dB per kilometer. After 100 kilometer, you are still talking about 20 dB loss, right? So there, you need to do this thing called quantum repeater, which is a little bit beyond what we can cover today. But the idea is that this quantum repeater is helping you to extend the range that this networking protocol can go. Okay. So we are mostly focused on solid-state device, solid-state platform for the consideration that we can make photonic or electronic devices on this solid state platform to control our qubit to do the communication, right? So out of many solid state platform, there are few of them that has this optical transition near this so-called telecom band where the transmission loss, the fiber transmission loss is low, okay? So you have this vanadium qubit in silicon carbide, you have erbium ions in some oxide material, and you have this series of deep color centers in silicon. And in our group, we focus mostly on this thing called T centers. Why we are so interested in the T centers? On one hand, is it has this telecom O-band optical transition, so you can naturally incorporate this T center platform with the existing fiber communication infrastructure. The other big motivation there is because of silicon, right? Silicon is a very mature material platform. It has gone through development for microelectronics and silicon photonics for the last, I don't know, like 60, 70 years, right? So that, in terms of incorporating devices, is a big plus. So let me give you a few examples how people do this device on other platforms, okay? So in these rare earth ions, for example, ytterbium or erbium, they are typically sitting in some oxide platform, okay? And then to make device of it, people can do many things, but majorly there are two ways. One is you fabricate the device on normal platform, let's say silicon on SOI, on insulator, which we call SOI. You fabricate that device, and then you do a transfer of that device onto the oxide surface so that this device can interact with the erbium ions inside the oxide, okay? Or you can do this so-called FIB, which is short for focused ion beam. You can mill a device structure like what you are seeing in this picture. For diamond, there are a few very promising quantum defects in diamond. People have developed similar techniques. For example, this pick and place. So this on the lower left side, this is called nitrogen vacancy in diamond. So what you can do there for device integration is to fabricate this diamond quantum circuit and then use a so-called tungsten tip to pick it up and then put it on another aluminum nitride-based nanophotonics circuit, okay? And of course, people have developed some other method where you can do some etching with some angles that you can form this silicon vacancy device array, okay? So all of this, they are very nice work in the sense that you can have very good quality devices, but they are all kind of not scalable or very challenging to do, okay? On the other hand, this is silicon, right? Silicon nowadays, people can do a wafer scale device fabrication, right? This is an 8-inch wafer, which is like this big, 200 millimeter diameter, right? And this is already like a routine thing people can do in the industrial foundry companies, okay? So that's as I mentioned, is a big motivation why we are so interested in color centers in silicon, right? Another, maybe a more subtle point here is that whenever you have a qubit, you need to deal with this process called decoherence, meaning that the environment is generating a noise that affecting your qubit, okay? One of these noise source is called nuclear spin. Each nuclear spin, you can consider it as a small magnet, right? If you have a qubit level, like let's say a 2-level system, these small magnets keep fluctuating and causing your 2-level system to drifting up and down constantly, right? This noise causing your qubit to decohere. So silicon, if you look at the isotope of silicon, there are 3 isotopes: silicon-28, silicon-29, and silicon-30. So there are, in natural silicon, there are about 5% of silicon-29, and this silicon-29 has nuclear spin. But people have developed ways to isotopically enrich silicon so that you can make a silicon material that only consists of silicon-28, okay? This is a similar process as how people do enrichment on other elements, for example, for nuclear power plant, right? Or some other scenes that if they want a specific isotope, they can do this enrichment process. So in our group, we have developed this material stack where we start with some commercial SOI wafer. We polish down first, and then we regrow enriched silicon-28. And then we can confirm from this mass spectroscopy measurement that this piece of material on the top, the device layer, the silicon-29 now is 40 ppm. So ppm is parts per million, right? So 40 ppm is, instead of 5%, now is 4 times 10 to the minus 5, okay? And this color centers in silicon is not actually a new topic. So here I'm showing you a review paper written in 1973, where people already start to see this kind of sharp emission lines below the silicon band gap, okay? At that time, people call this radiation damage centers because they typically show up when you shine, for example, electron beam or proton beam or neutron beam on your silicon material. And at that time, people are not so focused on quantum applications, right? There, people focus more like light emission, because silicon itself is a very inefficient light emitter because of the indirect band gap, right? So if you can have these sharp emission lines, people may be able to make a LED or even a laser out of silicon, okay? But at that time, no one think about like, oh, can I use this thing as a qubit for quantum applications, okay? So starting about around 2020, people kind of revisit all this literature and find out, oh, there is already this nice quantum defect inside silicon. So there are a bunch of them, actually. As you may notice, at that time, people decided to name these color centers using the letter, right? It's C, G, T, W. So here I'm listing 4 color centers in silicon that has emission wavelengths around the telecom band, okay? So T center is also one of it. So we are particularly interested in the T center, mostly because the fact that on the other 3 center, W, G, and the C center, their ground state is a singlet, which means that you cannot make a qubit out of it, right? So a very simple case of a qubit would be you have a spin up, you have a spin down, right? You call it 0 and 1, this is your qubit. But that requires you to have 2 states to be your qubits. But if you have a singlet state, you cannot make 2 states out of it. But T center has a ground state spin of 1/2, so which means that if you apply a magnetic field, this 1/2 electronic spin will be split into up and down, and we can utilize that as our qubit. Okay. And this has been kind of we call it like a hot area, because people start to realize the potential of this T center, and now there's a global effort on this color center, on T center, and also on this color center in silicon research in general. Okay, so these are kind of a background introduction why we care about T center and why what we can do with it. Okay, so then I'll spend some time to kind of introduce a little bit more about what we are doing in our group. So as you can see, there are 4 kind of big categories. One is we want to develop this so-called spin photon interface in silicon. So not only T center, but also some other potential quantum defects. So this spin photon interface, you can consider it as a way to kind of interact or talk to the spin. So the spin is your qubit, right? But what you can do to talk with the qubit is to shine lasers and then see what's the response, right? You can measure the spin, you can manipulate the spin, and then you can entangle the spin and the photon so that later when you send the photon from A to B, that photon can carry some information of your spin. So this is what we are trying to do in the quantum networking procedure, okay? The other big chunk of our research is to play with this quantum optics system. So The T-center has some limitations. For example, the low Debye-Waller factor, which means that there's only about 23% of the emission is going into this so-called zero photon line. And we want to enhance that, and also we want to accelerate the fluorescence emission. So what we do is we put the T-center in some kind of a photonic cavity, and then we use this thing called Purcell effect to accelerate this fluorescence emission process. And on the third part, we kind of utilize the fact that this is based on the silicon platform, so we want to combine different type of devices so that we can control the T-center better, and then we can utilize the T-center better. So here we're talking about not only the photonic devices, but also some electronic devices here. And then on the last part, with collaboration with Professor Guido Pagano from physics department, we are also thinking about how to make a hybrid quantum network between a trapped ion platform and the T-center. Okay. So the first part, spin photon interface. Okay. So what we do in the lab on a routine base is to do this so-called photoluminescence excitation spectroscopy. So many of you may heard the photoluminescence spectroscopy, where you shine a above band laser and then you see the fluorescence out of your material. So this PLE spectroscopy, the only difference is that instead of using an above band excitation, now you are using a resonant excitation. Okay, so now you can see the kind of absorption structure of your defects. And so we generate short laser pulses by using some combination of the electro-optic modulator and the acoustic optical modulator, right? And then we do this filtering of the laser by gating the single photon detector. So you don't turn on your detector when the laser is shining. You only turn on the detector when the laser pulse is finished, and then you start to see the fluorescence, okay? And then you can scan your laser frequency, and then whenever there's a T-center will absorb and then emit, you see a peak. That's what you are seeing in this spectrum. Those single kind of peaks are single T-centers inside the material, okay? And we can split the line in this question.
So it's a bulk material, and you have multiple T-centers.
Yes.
So are those peaks like a collective response of all the T-centers, or?
Exactly. So we will show the device a little bit later slides, but here we are looking at you can consider as an ensemble of T-centers. But this ensemble of T-center, each T-center may have slightly different optical transition. So on the x-axis, that's frequency, meaning that different T-center has a different emission wavelengths or emission frequency. Yeah, but you are seeing the collective behavior of the T-center ensemble. Yeah. Okay. Yeah. So if you apply a magnetic field, as I mentioned, the ground state of the T-center is actually a spin half system. Actually, excited state also spin half. So now instead of a single transition, you will have 4 transitions, right? Now it's 2 times 2. And then by doing this sideband generation using the electro-optic modulator, you actually address the 2 transitions simultaneously, and then you see that this splitting is increasing with the magnetic field, which is shown on the lower plot. That shows that the line is actually splitted due to the magnetic field, and this is called Z-man effect. With this spin photon interface, as I mentioned, one important task we are trying to do is called spin photon entanglement generation. So here it is very important because it's kind of the step number 1 if you want to do any communication protocol, right? So what you can do is you can combine some optical excitation and microwave control sequence as shown on the top panel of the right figure. And then when you send the photon out, you actually generate an entanglement between the spin and photon. So spin, you can understand it as spin up, spin down. And then the photon, the way to encode the photon is to have this thing called time being qubit. So you can actually generate qubit state of the photon by calling it whether it's an early arrival photon or it's a late arrival photon. So this early and late quantum state, you can also encode information, okay? And then of course, once you generate it, you want to use this so-called, we call it like, it looks like an interference measurement, right? So this is called Hohmann-Mandel interferometer to measure this spin photon entanglement. As I mentioned, for T-center, we first start with this ensemble measurement, right? We scan the laser frequency and see where the T-center is. And then we can then bring the cavity here to kind of interact with the T-center, okay? So here I'm showing you, we call it like our championed cavity coupled T-center. It has the highest per cell enhancement on the right side. So on the right side is showing you after the cavity is tuned with resonance with the T-center, what is the emission rate compared with the emission rate when there's no cavity. So you can see that with the cavity, you enhance this emission rate by a factor of 44. Questions?
It's a probably nice question. So I think I missed the part about how you create the cavity. So
oh, I will talk about that in the later slides.
So
yeah.
there is a cavity that I should assume, and then do you place a sample inside the cavity, or how does that work?
I will show you in the later slides, okay? So this is one example of the T-center, right? It has a line width about a gigahertz, and then we can accelerate the fluorescence emission so that the lifetime is about 20 nanoseconds. And in the middle, you show like if we keep looking at this T-center transition, how it moves, how stable it is along the time, okay? So these are a quick overview of the T-center part. We also have an effort on trying to find other potential quantum defect in silicon. So we built up this cryogenic. So here is PL spectroscopy actually. So build up this spectroscopy setup. Basically, you have a broadband laser, and then you shine onto your sample, and then you see the fluorescence. So for example, on the T-center, you see this spectrum, right? So we are talking, the main peak is the ground state to the first excited state, and then there's a small peak actually generated from the second excited state, okay? And we want to utilize this setup to look for new defects because T-center itself is not 100% perfect. So we are hoping that we can find even better quantum defects in silicon. And of course, it's not totally random hunt, right? We have some support from the theory. So people have utilized this thing called density function theory to calculate what type of quantum defects you can have in silicon and what property those defects will have, right? So in our case, we hope we can get telecom band transition, right? We hope we can get non-singlet ground state spin manifold, right? So those conditions can be included in the DFT calculation. So once the theory can tell us what defect is promising, then we can try to generate it and then try to measure and characterize with that. So the second part, as I mentioned, we spend a lot of time playing is this quantum optics or cavity QED, meaning that we try to put the T-center inside the cavity, and then the interaction between the cavity and the T-center can give you some effect, for example, the Purcell effect, where you can utilize to accelerate the fluorescence emission. Okay, so some of you may be familiar with this topic. If you have a two-level system in a single-mode cavity, you can describe it using this Jennings-Cummings model, where you have the energy from the atom, you have energy from the cavity, and also the interaction between the atom and the cavity. So that's the term G here. So G is kind of the interaction between your atom, this two-level system, and the cavity. Okay. Of course, your cavity has some loss and then some waveguide coupling, so those can be included in the model. And then at the end of the day, we will use this Lindbladian master equation to solve the dynamics of the system. So basically, you can initialize your system to an initial state, and then you let the system evolve. Then you can compute what's the cavity photon number, what's the population of the T-center, and then extract the information you want. So this is one example. So if you put the T-center inside the cavity, so the cavity we use is called one-dimensional photonic crystal cavity. So essentially it's just a nano beam with periodic holes punched through on the nano beam. And of course, you need to control the spacing of the hole, you need to control the size of the hole to create a correct band structure to confine the mode there, okay? So we measure a cavity coupled T-center by measuring, for example, the cavity enhanced fluorescence emission rate. So what you are seeing in that plot is that we tune the cavity across the T-center transition. So when we say cavity detuning is 0, that means the cavity and the T-center is aligned with each other, okay? When they are aligned with each other, you see that the enhancement is the maximum, right? And then when you move far away, it kind of decay in a Lorentzian. So this shows you that this enhancement, it is an effect of the cavity coupling. And this is very famous phenomenon called Purcell effect, okay? And we can use this numerical cavity QED model to explain everything we saw in the experiments. And this part, actually, there's a lot of physics behind it. Like, for example, one thing we are quite interested in the future is to utilize this cavity to create this thing called multi-qubit gate. So when you're trying to do the quantum networking and trying to do this, I guess I briefly mentioned quantum repeater devices, there's one important requirement there is that you should have the capability to do so-called Bell state management. So this Bell state management requires you can do some kind of 2-qubit gate between your in your quantum repeater devices, right? So one way to realize that 2-qubit gate is to utilize the cavity. So imagine the two T-center are resonant with the cavity, and then both are strongly coupled with the cavity. Then by exchanging cavity photon between the two T-centers, you actually can generate interaction between them. Once you have the interaction, you can utilize this interaction to build up your 2-qubit gate operation out of that. So this is a very interesting kind of application of this cavity QED dynamics. I want to show you a quick example how actually we can use this cavity QED to help us to read out the T-center spin. So as I mentioned, the spin is your qubit, right? You can do operation on the spin, but at the end of the day, you want to measure it. You want to know what is the spin population. Is your spin in 0 or is your spin in 1? Okay, so utilizing this cavity coupling, you actually can help to read out the spin in a very efficient way and a very kind of accurate way. So you have this, so because now we are talking about spin, so you cannot no longer just use the 2-level system. So now you have this 4-level system, which you can generate it after you apply a magnetic field in your device. And you can build up this system Hamiltonian now, which of course is slightly more complicated than the Jennings-Cummings model because now we are dealing with 4-level systems. And again, you can try to solve this Lindbladian equation to figure out the dynamics of the kind of the cavity QED interaction. Okay, and one thing we can utilize is that if you can pick up a really strong interaction between the T-center spin and the cavity, you can reach a regime where the T-center spin state is able to affect the cavity reflection. Okay, so in this plot you can see that there's there's an orange and blue, right? So if there's no T-center inside the cavity, if you try to measure the cavity reflection, you will see the black dashed line. So that's a typical Lorentzian shape of your cavity. Okay, but now if you have the T-center spin inside and the T-center spin is strongly interacting with the cavity mode, then depending on what spin state the T-center is, now if you try to measure the cavity reflection, you will see these extra dips showing in this orange and blue. So now if you can have this picture, you can easily imagine that I can try to read out the spin by just measuring the cavity reflection, right? For example, if I park my laser at around 0.5 gigahertz, right? If I park the laser here, then if I see a low reflection, I know that the system is a spin down state. And if the reflection is high, I know that the system is in the spin up state. So this gives us a way to quickly measure the T-center spin state here. And here are some kind of final result. Actually, utilizing this scheme, you can reach really high readout fidelity within relatively short readout duration. So for example, if you shine a laser pulse with 47 microsecond wide at power around 3 picowatt to this system with system parameters shown here, you can actually read out with accuracy of 99.8%. So that number means that if you do, say, 1,000 times of this measurement, there are only 2 times you're going to measure it wrong. The rest, 998 times, will be correct. Okay, so that's what does it mean? What it means for this fidelity. Okay, and of course, if you can sacrifice a little bit of fidelity, you can actually push this readout even faster, like with 4 microseconds. I guess the number and details are not so important here for you guys. The key point here is that with the help of the cavity, you can do a lot of things, right? This readout is one thing. You can also, as I mentioned in the previous slide, you can try to implement this multi-qubit gate with the help of the cavity. Okay, that's the main point here. Okay, sorry.
Is there something in your system that controls the readout time, the optimal time that you want, say, the one that you need for the highest?
That's more like the optimization process. It's not something like the system changed by itself. It's more like, okay, I can try to generate a laser pulse with 4 microsecond width or 10 microsecond width or 40 microsecond width. I try all of them, see which one gives you the highest fidelity.
But the choice, like whichever frequency gives you the best fidelity, shouldn't that be controlled by the system properties that you're trying to measure?
Yeah, to some extent, I think yes. So basically, based on the system parameter, for example, what is the Q factor of your cavity, what is the line width of the T-center, you can actually first calculate which pulse width will give you the highest fidelity. And then in the experiment, you can just use that pulse width to get the highest fidelity. Yeah. Mm-hmm. Okay. The third part of our research, again, is as I mentioned, is about this kind of silicon photonics. We call it silicon photonic chip. Actually, is more than photonics. We later also incorporate some electronic devices. But this schematic shows you how our kind of device work, right? So we have nanophotonic device fabricated on this so-called silicon on insulator platform. So you have a very thin silicon device layer, about 220 nanometer, on an oxide, which is typically on the order of like 2 micron. And then you have the substrate of silicon. So this is called SOI. So we fabricate the nanophotonic structure on the device layer, and then we patent it, we kind of etch the device, and then this is what we are using now in the lab. So on one end, you see there's a square that's called grating coupler. It is used to convert the free space light into the waveguide mode. And then the free space light is actually delivered by this angle polished fiber. Okay, so imagine you have a fiber, and then you polish at 45 degree, right? If it's 45 degree, when the light hits the interface, it will totally internally reflect it and come down vertically. Okay, so now by changing that 45 degree to say 40 degree, 39 degree, 41 degree, you actually can change how the angle of the light coming out of the fiber, and then you can design the grating coupler so that the diffraction angle of the grating coupler is matching with that angle. This is how we deliver the light into the system. Okay, and then on the other end of the device, you have this 1D photonic crystal, right? This series of holes on that 1D nanobeam. So that's our cavity. And because this is silicon photonics, you have you can do a large scale fabrication actually on this small piece of silicon is 4.5 millimeter by 4.5 millimeter. We have about 120 devices on that line. Okay, so that kind of colorful line, that's the kind of the diffraction color in the room light environment due to the grating coupler. So the grating coupler can perform very well. The one-way coupling efficiency can reach about 60%, which is relatively high. And then the Q factor of the device can reach about 100,000. We also have microwave devices. So we actually glue the fiber on a PCB, and then on the top of the on the front end of the PCB, we have a wire bond. So you see that curve. That's a 25 micron diameter gold wire, which we use as an antenna, so we can send microwave into the system to drive the spin transition. Okay. And as I mentioned, this is silicon photonics. So people know how to do kind of large-scale silicon photonic devices. Actually, whatever you can imagine, people probably know how to do it in silicon. So here I'm just showing you two types of device that we have been using in our lab. On the left side is the one with that schematic, right? On one end you have the grating coupler, and then the other end is that 1D photonic crystal. Recently, we moved to the, we call it like a second generation of the devices, where instead of one grating coupler coupled to one cavity, now you have an array of this cavity coupled to the center. We call it bus waveguide in an evalescent way. Okay, so now a single grating coupler can talk with all the cavities on the both sides of the bus waveguide, which can be a large number. So we can incorporate or fabricate about 30 cavities on both sides of this bus waveguide. So now a single grating coupler is simultaneously coupled with these 30 cavities, and then you can kind of talk to different cavities more easily compared with the left side, because left side, a single grating coupler only talk to one cavity. Okay. As I mentioned, silicon is not only a good platform for photonics, it's even better platform for electronics, right? So one thing we have been pursuing in the lab is to make some devices that enable us to do the electric field control of the T-center. So the T-center has the property that it has the electrical dipole moment. So when you apply an electric field, you actually can change the optical transition frequency. So this is called DC Stark effect. Okay, and the reason why we want to have that electric field control is to, on one hand, tune the T-center optical transition in case we want to match the optical transition frequency of two different T-centers. Okay. The other thing we want to try with the electric field control is trying to stabilize the T-center optical transition. So T-center has a little bit issue with this thing called spectral diffusion. So spectral diffusion means that if you have the T-center and then you try to measure it, the line can move around very fast. In one of the slides previously, I showed you the measurement of a T-center emission along like a few hours, and you don't see any movement of the line. That is because we believe that the spectral diffusion of the T-center is much faster than our measurement scale. So in that measurement, you already are measuring the averaged out line with shape, right? That's the reason why it doesn't have this spectral diffusion. So what we do here is we actually pattern and deposit gold electrodes on both sides of this cavity, and then we apply a voltage on top of that, so that we can generate electric field between these two gold electrode, and this electric field can interact with the T-center and try to control the T-center transition. Of course, this requires a little bit complicated fabrication process where you need to align your different layer of writings in the clean room. You can simulate. Actually, we have gone through this process, and then figure out that if you apply about 200 volts on this electrode, you can generate about 11 megavolt per meter electric field. And we hope that this electric field is so large that it can deplete the charge noise around the T-center. Okay, so the charge noise around T-center is actually the source of the noise that causing the spectral diffusion of the T-center. Right, this is how the actual device looks like. So we fabricate these electrodes on the SOI platform, and then we do the wire bonding to connect this device to the PCB. Okay. In the future, we want to go even more. Right, this is silicon platform. We can incorporate many different type of devices on the platform. So here is a kind of a envision or a future plan, if you want. So what do we want to do is we want to have qubit on the silicon chip. At the same time, we want to have other type of devices, for example, modulator, phase controller, a switch, right, and even the single photon detector on the same chip, so that we can just control this chip electronically. So this is more like a computer chip. Okay, the difference is that now you are using a qubit to do your kind of local operation rather than using transistors in your laptop or iPad to do the computation. Okay, so this is one future kind of plan that in our minds based on this T-center platform. Of course, here there are some other device challenges. For example, how you do the modulator at the cryogenic temperature, because the T-center work at 3 Kelvin, which makes this modulator a little bit tricky, because at the room temperature, silicon you can just heat up. When you heat up the silicon, the index change. That index change can be utilized to do some modulation. But when you go to the cryogenic temperature, this thermal optical effect gets 4 order of magnitude smaller. So you cannot really do temperature control there. And you want to find some other ways of creating this index modulation and then change the silicon device performance. And as I mentioned, we also want to have the nanowire single photon detectors there. So people have tried to patent this superconducting nanowire there. So the idea there is that if there's a single photon being absorbed by the superconducting nanowire, it will break the superconducting phase of this nanowire. So now if you flow in a current through this nanowire, you will see a voltage spike whenever the photon is being absorbed and then breaking the superconducting phase. Okay. So these are the part number 3, where we want to utilize the silicon as our platform to hold this many quantum components to make a quantum photonic chip. The last part is about this hybrid networking. So as I mentioned, this is kind of like our, 20-year plan or something. We want to build up such a quantum network so that we can incorporate different quantum platforms into this networking system, so that we can combine the, for example, advantages of superconducting qubits and the advantages of trapped ion platform. So here, what we have in mind is to implement this so-called memory-enhanced communication. So one way people typically do for this remote entanglement generation is, let's say, Alice and Bob each send a single photon into the center measurement station. And then if you do this Holm-Mandel 2-photon interference measurement, you can actually project the spin state of Alice and Bob into some kind of entangled state. Okay? But that requires the 2 photons arrive in the middle station simultaneously, which can be tricky in the real application. So the memory here, what it does is that the memory can store, let's say Alice photon arrived first. The memory can store that information for a little bit of time, which is basically how long your memory can stay, right? And then during that time, as long as the Bob's photon can arrive, now you can do this measurement. So here, you don't need to let the 2 photons arrive simultaneously. It's kind of like the memory create a buffer, and this buffer helps you to increase the successful rate of this measurement. Okay, and then again here we're gonna do this so-called time beam encoding of the single photon. So as I mentioned, we are collaborating with Professor Guido Pagano from physics department, they have a platform, trapped ion platform based on calcium, and they want to put this calcium ion into this is called a bow tie cavity to extract the photon efficiently, and then they want to encode this photon, which is basically entangled with the calcium ion spin state, and then send a single photon to our lab, and then to interact with the T center. The final goal of this project is that by doing this process twice, let's say you have 2 calcium modules in Guido's lab, for example, each of them send a spin-entangled time-beam photon into our lab, and then we use the T center to kind of entangle these 2 different calcium modules, so that these 2 calcium modules now can build up entanglement through the T center. Of course, on benchmarking testing, this can be implemented as, for example, Guido's lab has a chamber where you have 2 ions, right? You couple the emission of the 2 ions separately, and then via fiber into my lab, and then we can entangle via the T center. In the future, the picture will more like, let's say, there's another trapped ion platform in Austin, and then we have a trapped ion platform in Houston, and then we can utilize this T center to kind of connect these 2 different calcium ions into the network, and then let them entangle, and then to do some quantum communication. Okay, so this is an ongoing effort, and we are hoping we can extract some useful outcome from this project. Okay, towards the end, I want to maybe advertise my courses a little bit. So I'm teaching 2 courses that are relevant to graduate students. The first course is called Introduction to Quantum Computing with QED. So actually, I saw many students here took this class. So this is a class where it tells you how to utilize this platform developed by IBM called QED to encode or to compute some of the simple circuits, like the one I'm showing in the middle, right? And then in this course, we will talk about different quantum algorithms. For example, a Shor's algorithm, many of you may have heard of that, right? And Grover's algorithm, right? To see that how quantum computing can help you to accelerate the process or solve some problems that classically is very tricky to solve, okay? And then in this class, we're gonna utilize the real quantum computer from IBM. So actually you can kind of encode your problem into the quantum circuit, and then you can submit the job to IBM Cloud Service, and then they will run those circuits on their real quantum computer and then feedback with you the results. So it's a quite interesting process there to really use a quantum computer. So here we're not talking about simulation, we are talking about run this circuit on the real quantum computer, hardware quantum computer, and then see what's the results, okay? So this is a course both the senior undergrad students and the early graduate student can enroll. But the second one is called Introduction to Quantum Information Science and Engineering. This is also one of the core courses of the NRT program in the Applied Physics program. So in this course, this is a graduate level course. In this course, we will talk about some fundamentals about quantum information processing, and then we'll spend the majority of the semester to talk about different leading quantum platforms. How does it work, both from the physics point of view and from the engineering point of view, so that after this course, you will get some picture of each platform. Of course, this course will not dive too deep on each platform because the way it is designed, but it will give you the capability to start looking into this platform on your own by reading some literatures, okay? So these are the 2 courses on the graduate kind of relevant sense. With that, I want to stop here, and I will land on these slides for more questions.